there's a Mac version and a Windows version that I posted, so you make sure you're installing the right one. I'm going to skip this syntax bit and just go right into the code. So I'm going to use the 2 product 3 machine problem that we did last class. You have to determine how many product 1 to produce, how much product 2 produce. Producing the products requires hours of machine 1, 2, 3. You have 4, 12, and 18 hours available on machine 1, 2, 3. And each product 1 generates $2, product 2 generates $5. So the model that we had from last time was to here. Right? Xi is number of product I to produce, so it's X1 is 2. Maximize the revenue, subject to machine 1 hour, machine 2 hour, machine 3 hours, cannot produce negative amounts. And this is what you type into the lingo, right? You start with a model statement, you end with the end, and then you type your equations, right? You type your equations. You can give them a label or a name if you want, right? And then you just solve it. So let me open up my lingo over here. When you open it the first time, it'll ask you for a license key. Just click demo, okay? So this model editor window's open, and so for you to start typing in your model, right? But in the interest of time, I'm just going to cut and paste from the Word file over here. Okay, so you type in your model, and then you click on Lingo and solve. Oh. Why is it not sending? You guys need to say something early. I guess you're falling on your laptop thing. I guess it's fine, right? Okay, so I cut and paste in, and to solve a model, you click on Lingo and solve, right? Or you can click on this solve button over here. Does the same thing. Okay? So you click on Lingo and solve, it solves the problem. It tells you that, okay, your model is an LP, linear programming. I found an optimal solution. Maybe your model is infeasible or unbounded, it'll tell you that. Okay? And then the objective value, that's your objective function z, right, is 36. And then the optimal value of x1 is 2, and the optimal value of x2 is 6. So it's pretty simple, right? You type in your equations, you click on Lingo solve, and it solves the problem for you. Okay, so let's look at over here. So there's a few things to notice. One is that normally we would put maximize z. You might notice here there's no z. Okay. The other thing we normally write is the x1, x2 greater than equals 0. And you can see no need. The variables being positive is so common, Lingo just assumes it. Okay, so you don't need to bother with there. There is semicolons that students will forget and get error messages. Those are the main things. Okay? Also, if you label your equations, the labels show up in the output. So if you label your equations, the label shows up double. Otherwise, it'll say row 0, 1, 2, 3, and you'll then say, what is row 3? Okay, now you know, oh, this is the constraint for machine 3, right? So those are the things. No Z. Don't bother with the putting down the X positives. Make sure you got your semicolon. Oh, one last thing, very important. You need the star. You cannot just write 5x2. Okay? You need the star. Right? Okay, so once we have the output, we can answer questions, right? What's the optimal solution? Revenue, number, plot 1, 2 to make. Okay, so revenue is just the objective value, and you can see that it's 36. Product 1 is the variable x1, we see it's 2. And then product 2 is the variable x2, and we see it's 6. Okay, easy to read the answer. What does the slack surplus mean? Well, we talked about slack and surplus last time. Basically, for machine 1, the slack surplus is 2. That tells me there are 2 unused hours on machine 1. The slack or surplus on machine 2 is 0. Tells me there's 0 unused hours on machine 2. How about dual price? We talked about dual price last time. For machine, we calculated the dual price for this problem for machine 1 and 2 last time by manually. But, so the dual price for machine 1 is 0. So it tells me that if I increase machine 1 hours, Z is not going to change, right? Z increased by $0. The dual price for machine 2 is $1.50. So it tells me if I increase 1 hour on machine 2, then Z is going to go up by $1.50. The dual price for machine 3 is 1. So that tells me if I increase machine 3 hours by 1, Z will go up by $1. Right? How much would you be willing to pay for 4 hours on machine 2? Well, basically I have 4 hours. The dual price for machine 2 is $1.50. And so you would want to pay up to $6, right? So every hour I get $1.50. So naturally I would pay no more than $6. And we talked about there's a range, right, for this $1.50 to be $1.50. I cannot give you 1,000 hours more in machine 2 and expect you to make $1.50 for every of those hours. We talked about that last time. There's a range. And the range from last time was as long as it's between 6 and 18 hours, the dual price for machine 2 is $1.50. But how do we do that? So we can use the range analysis feature in Lingo. So first you have to enable it, and then you have to, run it, right? So let me show you that. So let me close this here. So first I have to enable it. So according to the step, you click on Lingo and Options. Then you select this General Solver tab. And then where it says dual computation, right now for you it'll say price. So you have to change it to price and ranges. Okay, this dual computation box over here. And then you say save and OK. Then you run your model so that the data kicks in, so you solve. And then you close out this window, you go back to your model screen, and then click on Lingo, and instead of solving, you choose range, and then this range analysis information shows up. Don't worry, I got a little Lingo exercise here for you to do next so that you can practice all that. So, what is the range for machine 2? What is the range for machine 2 hour for which the dual price is going to be $1.50 for machine 2? So we'll be looking at the right-hand side ranges for machine 2. Currently, it's 12, and you can see in the model, currently for machine 2, it's 12 hours, right? That's the current value, or original value. You can decrease by 6. or you can increase by 6. So as long as machine 2 hours is between 6 to 18, the dual price is $1.50. What is the range for machine 1? However, the dual price will remain 0 for machine 1. So I'll be looking at machine 1 this time. The original value is 4. Right? Again, you can see from the problem, the original value is 4. And then you can go down by 2. You can go up as much as you want. So as long as machine 1 hours is between 2 and infinity, the dual price is equal to 0. Question 2, what is the range for the price of product 1 for which the current solution will remain optimal? Okay, so the objective function was maximize z 3x1 plus 5x2. So we're looking at the price for product 1. So we're looking for the range of the price of product 1 for the current solution remain optimal at x1 is 2, x2 is 6. So basically it's like the golf bag, deluxe bag, standard bag thing, except now we're doing it with lingo. Okay, so we would be looking at the objective function coefficient ranges now. And we're looking for the coefficient for the variable x1, so we'll be looking at this here. So the current value is 3. Current value is 3. You can decrease by 3. You can increase by 4.5. So the range is between 0 and 7.5. So as long as this thing is between 0 and 7.5, the current solution is going to be 2 and 6. Okay, so that's the kind of things you can do with the range analysis feature in Lingo. So now your exercise with Lingo. And your exercise is to solve Geopedo and answer some questions. So we never really solved this problem. I just gave you the answer. So now you get to solve, okay? So how many toy soldiers, wooden toys, ex-soldiers, and trains produce? And then answer the 3 questions. Okay, I'll come around if you are not able. So if you want to label your constraints, these labels cannot have spaces. So you cannot say max space 3. You have to put it all in one. Or you could put max underscore 3, but you could not have max space 3, right? Okay, so maybe I will just put it in a Word file, that way you can see it bigger. Okay, so that's the model, nothing fancy, right? And then, of course, to solve the problem, you can click on the target solve button, or you can click on your lingo and solve. So we have an LP problem. They solved it global optimal, so optimal found, and the objective value is 180. Right? So you can close this. And if I were to cut and paste it over to the handout here. Okay, so we see that the objective of the Z value is 180, so the profit is 180. We see that the optimal value of X1 is 20, so make 20 soldiers. The optimal value of X2 is 60 trains. Now, the question asks you, what is the revenue from trains? Well, it's not there, but you are making 60 trains, and so each train gets what? $2. So 2 times 60, so the revenue from train is $120. B, are there any unused carpentry hours? So I would be looking at the slack surplus for carpentry, and the slack surplus for carpentry is 0. So the answer is there are 0 unused hours. Okay? I used it all up. There are 0 unused hours. Then part C says the profit for product 2 is $2. And how high can this go, or how low can this go for you to still be producing 20 soldiers and 60 trains, or the optimal solution remains unchanged? So how high can this 2 go or down? So this here, I would need to run my range analysis. So you can click on lingo and range. Okay, and then I would be interested in the so-called objective coefficient range. Okay, so I'm looking for the coefficient for the variable x2, right? The currently is $2. I can decrease by 50 cents. I can decrease by 50 cents, so that means on the left side would be $1.50. I can increase by $1, so that would be 2 plus 1. So the range would be $1.50 to $3, right? Okay, so maybe I'll just write this on the thing here. So solving the problem, the optimal solution is x1 is 20, x2 is 60, and z is 180. And as I said, revenue from train is equal to 2x2 any unused carpentry hours, slack surplus equals 0, so 0 unused hours. So from the objective coefficient range, you get 2 minus 0.5 and 2 plus 1, so the range is 1.5 and 3. Okay, so at least you get a little practice. You're gonna need it for your assignment too. Okay, then we have this final problem over here, we'll do together. So this final problem is this bluegrass farm. They're experimenting with creating a special diet feed for their horses. There are 3 feed products. So they can buy some pounds of standard, buy some pounds of enriched oat, and like some pounds additive. And then mix it up and feed to the horse, right? There's the cost per pound. Standard is very cheap, additive is very expensive. Each of the feed contains some amount of vitamin A, some amount of vitamin B, and some amount of vitamin C. Obviously, the additive stuff contains a lot of the more of the vitamins than the others. The horse has to eat a minimum requirement of 3 vitamin A, 6 vitamin B, and 4 vitamin C. And you cannot feed the horse more than 6 pounds of food. It can't eat that much food. So, how much standard, enriched, additive to buy, mix, feed to the horse, make sure the horse gets their minimum vitamin A, B, C. The horse cannot eat more than 6 pounds of food, and you want to minimize the feeding cost. So we'll let S, E, and A be the pound of standard, enriched, and additive to buy. And then we have our model here, minimize the cost, 25 cents, 50 cents, $3. Total vitamin A, at least 3. Total vitamin B, at least 6. Total vitamin C, at least 4. Don't feed more than 6 pounds. Total food, less than 6 pounds. Cannot buy negative amounts. And then we have our model here. So we have objective, ingredient A, B, C, and then the weights, all right? So very simple. So we can solve this model here with lingo and get the output. Okay, and then we can answer some questions. So there's my objective value, or Z. And then there's the optimal values of the variables. So how many pounds of additives should bluegrass use? What's the optimal cost? Well, we already see that the optimal cost is the objective value, and that is 5.97, right? Amount of additive should feed, well, there you go, 1.54 pounds. Then, if it is required to increase the horse feed by 1 unit of ingredient A, how much will cost go up? So right now, the horse is needs at least 3. So what if we have to feed the horse 4? How much will the cost go up? So we look at the ingredient A. Currently, it's 0.8S, 0.2E, greater than 3. But what if we have to change this to 4? What will you need to look at to answer this question? Yes? No. Yes? Dual price, right? Change right hand side, how much does Z go up or down, right? So we look at the dual price for ingredient A. So the dual price for ingredient A is minus 1.21. So the dual price is minus 1.216. So what does a minus dual price tell us? Well, from last week, if Z is better off, the dual price is positive. If Z is worse off, the dual price is negative, right? So better off, dual price positive, Z worse off, dual price negative. Okay, so that's what the negative is telling us, that Z is worse off somehow. So a negative dual price means Z is worse off. In this problem, you try to minimize cost. So worse off means what? Costs go up or down? Up, right? Means costs go up. And so costs go up by $1.216, right? How about the weight? Right now, we can only feed the horse 6 pounds of food. What if we're allowed to feed the horse 7? How much will cost drop? So we look at the weight constraint right now. We're allowed to feed the horse 6, but what if we're allowed to feed the horse 7? How much will cost drop? Again, we look at the dual price. Okay, so for the weight, the dual price is 9,189. So a positive dual price means Z is better off. So better off means costs go down. I think people might be surprised. And why would you be surprised? Because for most people, when you eat more food, your cost will go up. So why is it that when the horse eats more food, the cost will go down? Well, let's put it this way. If you can feed the horse more food, then you would buy more of this cheap standard stuff and feed the horse instead of having to buy the more expensive stuff containing more vitamins, right? So you're substituting by buying more of the cheap stuff, bigger amounts, so that the horse still gets the vitamins, right? If they can eat more. It's like you, right? You need a certain amount of beef. Okay, instead of eating a steak, you go eat 3 hamburgers. Cost gonna go down as long as you can eat 3 hamburgers, of course, right? So same idea. So the cost go down because you can feed horse more of the cheaper standard food. And then the final question over here. There we go. Okay. Oh. If it is required to feed the horse 1 unit more ingredient B, how much will cost go up? Again, right now we have to feed the horse 6 units of vitamin B. So what if we have to feed the horse 7? How much will cost go up? So we look at the vitamin B constraints over here. We have 1S, 1.5E, 3A, bigger than 6. And what if we have to change this to a 7? Again, you look at the tool price over here for ingredient B, and it's 0. Okay, it's 0. So the cost will not change. Why is it when the horse eats more vitamin A, the cost goes up by $1.21 something, but when the horse has to eat more vitamin B, the cost doesn't change? Okay? Why is it when the horse has to eat more vitamin A, the cost goes up by $1.21, but when the horse has to eat more vitamin B, the cost doesn't change? Why is that? Because we have a slack surplus. First of all, lingo is confusing. Is it a slack or surplus? So how do I know if this number means slack or does it mean surplus? Well, from Thursday again, slack is for less than equal to constraints. And then excess or surplus is for greater than equal to constraint. And for the horse here, it's greater than equal to, right? And so that value is a surplus. So this should be a surplus because the constraint is 1S plus 1.5E, and then plus 3A is greater than equal to 6. Okay, so we know it's 355 surplus. So what's that mean?
We have like an unused amount of 3.55.
Nope, it's not like we have an unused amount. For sure it's not unused. Yep.
It's a non-binding constraint.
Nope. Wait, trying to get it here already, so I better give you the answer. It means that the horse is eating 3.55 more than the minimum requirement of 6. It means the horse is eating 3.55 more than the minimum requirement of 6. Basically, it's eating 9.55 right now. And so when you make it eat 7, doesn't matter. It's already eating 9.55. It's already eating 9.55, right? So I'm gonna say here, there is a surplus equal to 3.55, means horse is eating 3.55 more than the requirement of 6. It is eating 9.55 right now. So no change when it has to eat 7. Okay, so that's how we determine why it didn't change, right? Again, assignment 4 is once, right? It's due.